Well, welcome back to our class on systems design as we're working through Dennis, Wixom, and Roth, their assessment of system analysis and design, primarily with a focus looking at information system the way it's presented here. I have several other classes that are related, things dealing more specifically with system engineering, as well as a class on software engineering. So you can keep that in mind and feel free to take advantage of that other content. And so we're now in the third phase of this. We're working through the design things that we're looking at. And for this particular lecture, we're going to be focusing on program design. And so that's what we'll get into here. So another important activity in the design phase is the designing the programs that will perform the system's application logic. Programs can be quite complex, so analysts or system engineers must create instructions and guidelines for programmers which clearly describe what the program must do. So this chapter in this lecture will describe the activities that are performed when the program design is developed. First, the process of revising the logical data flow diagrams, DFDs, into physical DFDs is outlined. Then two techniques typically used together for describing programs are introduced. The structure chart depicts a program at high level in graphic form. The program specification contains a set of written instructions in more detail. Together, these techniques communicate how the application logic for the system needs to be developed. And so the objectives is to be able to revise the logic DFDs to the physical DFDs, be able to create a structure chart, be able to write a program specification, be able to write instructions using pseudocode, and become familiar with event-driven programming. So that's the content that we're hoping that we'll master here. So in terms of an introduction, various implementation decisions will be made about the new system, such as what programming languages will be used. So there's a lot of things that can be thought about. You know, what is going to be the operating system? Is it going to be multi-platform? Things like that. The data flow diagrams created during the analysis phase are modified to show these implementation decisions, resulting in a set of physical data flow diagrams. The analyst or system engineers then determine how the processes of the system will be organized using a structure chart to depict their decisions. And finally, the detailed instruction called program specifications are developed so that during construction, the programmers know exactly what they should be creating. Well, let's think a little bit more about moving from logical to physical process models. During the analysis, the system analysts identify the processes and the data flows that are needed to support the functional requirements of the new system. These processes and data flows are described on the logical data flow diagrams. The logical data flow diagrams do not contain any indication of how the system will actually be implemented. But during the design, the physical process models are created to show implementation details and explain how the final system will specifically work. So for the physical data flow diagrams, they contain the same components as a logical DFD. And so we'll, in a couple of charts, show that you can do a one-for-one mapping. The difference will be that the two models is that the physical DFD contains additional details that describe how the system will be built. And there are 5 steps to perform to make the transition to the physical data flow diagrams. Here are those steps. First, you add implementation references. 2, you draw a human-machine boundary. 3, you add related data stores, data flows, and processes. 4, we update the data elements in the data flows. And 5, we update the metadata in the case repository using our case tools. And so you can read more of the explanation here, or even better, go and look this up in the textbook and get some more information on that. So here is an example of the physical data flow diagram for the shop manager approval of a custom drone order. And this is a level 1 data flow diagram. And so this is for our drone tech example that we've been using all the way through our textbook, and we'll continue to now get more specific as we go. And here is a chart that where we can see the contrast difference between the logical and physical data flow diagrams for drone tech. And so the logical, it's more higher level, not as much details. And here we're seeing that we're starting to show the forms that need to be exchanged, more information about how the database is managed. And so we're using MySQL and stuff like that. So for designing programs, first of all, we want to be thinking about creating the instructions for the programmers. We want to think about the top-down modular approach where we begin with the big picture and gradually add detail. The program design document, this has all the structure charts and specifications needed by programmers to implement the system. And so we have that nice way of giving this interaction between various parts of the development team. So we can be thinking of using a top-down modular approach. And so here would be a way of thinking about that. So first, we understand the general context. So maybe we're going to be operating in the state of Virginia. Second, we break the contents into logical pieces. And so maybe we're talking about a general locale, a city, a county, or something like that. And then finally, we add details to each piece, the very more precise location, getting into part of a city, a suburb, or something like that. So how do we go about doing a good program design? First, the analysts create a high-level diagram that shows the various components of a program, how the components should be organized, and how the components interact. It's known as the structure chart. Next, the program specifications are written to describe exactly what needs to be included in each program module. A pseudocode is a technique similar to structured English that is used to communicate what needs to be written. And this is tied into a variety of classes. Data structures, especially, is one where you see that come up a lot. And so you're not talking about a specific language, but you're talking about the general algorithms and approach for implementation. At the end of the program design, the project team compiles the program design document, which includes all of the structured charts and program specifications. So let's get into structure charts. They're important program design technique. It shows all the components of code in a hierarchical format, the sequence, selection, and iteration, and it illustrates the organization and interaction of the different program modules. So here's an example for a structure chart. And so now we're thinking about an academic situation where we're trying to create a student grade listing. And so you need to be getting all of the records, the current GPA, cumulative GPA, and then the outputs you display, what the grades are, and if there are on the dean's list, that would be something that we would want to include. So here we're having syntax that we need to be abiding by. So we have two charts that will go over this. First, we have this, and so we have the chart element, and so we have a module, and so this is how we depict a module. We have a library module that's a more specific type of module. You notice that all these modules have numbers. You can have a loop, and so we're getting a chance to be seeing how information can flow. We can have a conditional line, and so there needs to be a decision, and then we know which path to take based on the answer of that decision. We can have a data couple, and so we can see a direction and an arrow. So there's a flow that we're trying to indicate. We can have a control couple, and so it also contains an arrow. So there's a slight difference between exchanging data and passing on the details of control. We can have an off-page connector, and so say if we're going to be printing a grade listing based on the example we showed a couple slides ago. And then we can have an on-page connector around circle. So that's the syntax that we're proposing here. You may get exposed to some other syntax, but that's what we want to be thinking about for this textbook, for this course, and for this lecture. So that's some highlights for a structure chart. In terms of the syntax, for the module, a structure chart is composed of modules. These are lines of program code that perform a single function. The modules are depicted by rectangles and connected by lines. The control module is a higher level component that contains a logic for performing other modules. The components that it calls and controls are considered subordinate modules. And at times, modules are standardized and used in many places through the system. So these are called library modules. We saw that in the table. And the lines that connect the modules communicate the passing of control. There are two symbols that describe special types of control. The curve, arrow, or loop indicates the extension of some or all of the subordinate modules is repeated, and a conditional line, which is depicted by a diamond, denotes that the execution of one or more of the subordinate modules occurs in some case, but not in other cases. So there has to be some kind of decision process. A circle is used to connect parts of the structure chart when there are space constraints and a diagram needs to be continued on another part of the page. In terms of couples, couples are shown by arrows are drawn in the structure chart to show that the information is passed between modules. The arrowhead shows the direction. Control couples drawn with the use of arrows with filled-in circles are used to pass parameters or system-related messages back and forth among the modules. And in general, control flags should be passed from subordinate to control modules, but not the other way around. So let's think about building the structure chart. The processes in the data flow diagram tend to represent one module on the structure chart. Afferent processes provide inputs to the system. Central processes perform critical system operations, and efferent processes handle system outputs. Each process of a data flow diagram tends to represent one module on the structure chart. The data flow diagram leveling can correspond to the structure chart hierarchy. The difficulty comes when to determine how the components of the structure chart should be organized. So this just gives some more information about how we go about the transforms and transaction structure. So here we can see different ways how we can be looking at those flows. You can see the textbook for more details. So let's talk about this. We'll continue with these next two charts to give some more specifics. And so a transaction structure, the control module is calls the subordinate modules, each of which handles a particular transaction. So here we can see how that breaks into four elements. Few afferent processes, many efferent processes, a higher level of structure chart, and concerned with the coordinating the production of outputs. So this is how we can see these various elements here: decision, and then we have up to four different things that are going to be pushed out. In terms of transform structure, the control module calls several subordinate modules in sequence. Each subordinate performs a step in a process that transforms an input into an output. So we would have many afferent processes, few efferent processes, so many inputs, one out, not few outputs. Lower level of a structure chart and a concern with using the inputs to create a new output. So we gather all this information, then we're able to display the desired outputs. So what are the steps in building the structure chart? First, you want to identify the top level modules and decompose them into lower levels. You want to be adding the control connections, adding the couples, and finally review and revise again and again until this is complete. So you can have an iterative process till you get to a final state that you're comfortable with. So back to our drone tech analogy, Here we can be thinking of how we would identify the modules and levels for the structure chart. So here we have the types of things that would be done for a drone flight request to the pilots. Next level is you notify the pilots of new flight request. The pilot submits a bid, and then you select the winning right bid. And so here would be the things, and then we have more details beyond that. So that's the first step, identify the top level modules. We can see this up here. Next, we want to be adding special connections to the structure chart. So now we get a little bit more specifics that we've started to add for what's the nature of how we push these down, and we're showing things at the down at this bottom tier. So we have the highest level is from the level 1 data flow diagrams, and here is from the level 2 data flow diagrams, and we get the final resulting things that we're starting to manipulate down at the bottom. Then for step 3, we add couples to the structure chart. And so now we get some more information about data flows of specific types. And that is something that we include. And so that's what we have. And then finally, we did what we talked about. We review and revise again and again until we feel that there's a sense of completion. So what are some design guidelines? High quality structure charts result in programs that are modular, reusable, and easy to implement. The measures will include cohesion, coupling, and approximate level of fan out and fan in. So we want to be looking to build modules with high cohesion. Cohesion refers to how well the lines of code within each structure chart module relate to each other. A module should perform only one task, making it highly cohesive. And so it has a standalone purpose that it's autonomous, if you will, in some ways. And there are various types of cohesion, some of which are better than others. So here are types of cohesion from good to bad. And so you have functional, sequential, communicational, procedural, temporal, logical, and coincidental. So this ranges from a module performs one problem related task for functional, for sequential, output from one task is used by the next. Communicational elements contribute to activities. Procedural elements are performed in sequence but do not share data. Temporal activities are related in time. Logical, we have a list of activities, which one is to perform. Is chosen outside of the module. And finally, coincidental, there's no apparent relationship. So you can see this cohesion from high to low. So here is a cohesion decision tree. And so does the module do one thing? Yes, and then it's a functional cohesion. Then we start asking the next level of questions. Well, if it's functional, we're done. If it doesn't, then how are they related? Then we go down to sequential, and we see whether or not it is, and then we gradually work down this tree from good to bad into the level of cohesion. So this is kind of a decision tree to help us figure out what it is, how we're going to categorize the type of cohesion we have. In terms of factoring, it's a process of dealing with low cohesion by separating out functions from one module into a module of its own. Separate tasks into different modules is what we want to always strive for, and we want to reduce the use of control flags. In terms of building loosely coupled modules, coupling involves how closely modules are interrelated. The second guideline for good structured chart design states that the modules should be loosely coupled. That way, modules are independent from one another. The number and kinds of couples on the structure chart reveals the presence of coupling between the modules. And so just like we talked about cohesion, now we have types of coupling from good to bad: data, stamp, control, common, and content. And so for data, modules pass fields of data or messages. For stamp, The modules pass record structures. Control modules pass a piece of information that is tended to intends to control logic. Common, the modules refer to the same global data area, and content modules refers to the inside of another module. So you can see going from good to bad as we work our way down each one of those. What about fan in and fan out? Fan in describes a number of control modules that communicate with a subordinate. A module with high fan in has many different control modules that call it, and this is a very good situation. Structures with high fan in promote the reusability of modules and make it easier for programmers to recode. And we want to avoid a large number of subordinates associated with a single control, that is fan out. So we see a high fan in with that, and then that would be over here, and a low fan in, a one-to-one relationship we're seeing on the left. Here is an example of a high fan in. So that's how that would look. And here we're seeing an example of a low fan in. So those are some possibilities, and when we're starting to build some of this documentation and diagrams, we can do some assessment of where we think we're in a good place and aligned it towards the design principles we want to be working with. So what is a checklist for a structured chart quality? The library modules have been created whenever possible. The diagram has a high fan-in structure. Control modules have no more than the 7 subordinates. Each module performs only one function, so that would mean it has high cohesion. The modules sparingly share information, so loose coupling. Data couples that are passed are actually used by the accepting module. The control modules are passed from low to high, and each module has a reasonable amount of code associated with it. Well, what about the program specification? So for this, the argument is there is no standard approach. It includes program information. You want to note events that trigger actions, you want to be sure to catalog and list the inputs and outputs. Including pseudocode is going to make it easier for this to be codified when you get into programming, and you want to provide additional notes and comments as needed. Here's just an example of a snippet of pseudocode that you could be using. And so this is a calculate the discount amount. So say this is something that you want to be using. So 10%, 20% discount or none. These would be the kind of options that we could be considering. This is just a screenshot from the textbook of a sample program specification. And I'm not going to go through this, but this is just some more details from the textbook that I'd refer you to. All right, well, let's just finish up with a chapter review, just have a couple of slides. So we've got a chance to consider how to identify and describe the 5 steps involved in converting the logic process modules to physical process modules. We describe the purpose and components of a structured chart. We explain the 2 primary structures shown in a structure chart and the purpose of each. We discuss the 4 steps involved in creating the structure charts. And we also explain the structure chart design guideline of high cohesion. And we looked at listing and discussing the 7 kinds of cohesion from good to bad. We explained the structure chart design guidelines of low coupling. We considered listing and discussing the 5 kinds of coupling. We explained how the concept of fan in and fan out pertain to the structure chart. We explained the recommended content of our program specification document, and we also described the pseudocode and explained how it differs from structured English and gave a brief example of what that looks like. We have some more terms that we have utilized in this chapter. And so this is the first of 2 charts that we have, and fan in and fan out, for example, were some things that we got a chance to be thinking about as we're looking at some of our diagramming. We once again have data flow diagrams, and what we're focusing on in this chapter is especially looking at the physical data flow diagrams. So, and also we looked at pseudocode, which is going to be very helpful for the coders that actually implement what we're creating in a specific programming language. All right, thank you very much. That's it for this lecture.